Good morning. Welcome back to the magnetic properties of matter. Now we are discussing about the Langevin's classical theory of paramagnetism, in which we are considering the paramagnetic material consisting of n number of atoms or molecules, and each atom or molecule is considered as a magnetic dipole. And these magnetic dipoles will be oriented randomly in the absence of any external magnetic field, in the absence of B. When we apply an external magnetic field B, these magnetic dipoles will themselves align in the direction of the magnetic field. We have considered n number of dipoles, so n is given by the expression n proportional to exponential minus e by kt, or n will be equal to a constant c into exponential minus e by kt. Right? We know that n represents number of atoms or molecules of a paramagnetic material. In the sense, n number of permanent magnetic dipoles, since each atom or molecule behaves as a magnetic dipole. And E represents the energy of each magnetic dipole. K represents the Boltzmann constant, and T is the absolute temperature. As we know, C is some constant. Under equilibrium, right, the magnetic dipole will be oriented randomly. When we apply a magnetic field, the magnetic dipole begin to rotate, right, depending on the strength of the magnetic field. Now, at certain stage, the rotation of the magnetic field, the rotation of the magnetic dipole stops. At that case, we say that the magnetic dipole is said to be under equilibrium. Now, under equilibrium, let the magnetic dipole is rotated through an angle theta, as shown in the figure. PQ represents magnetic dipole, PQ represents magnetic dipole, and this is the direction of the magnetic field. This is the direction of the magnetic field. Because of the presence of magnetic field, the dipole is rotated through an angle theta, Now, because of which the dipole or the magnetic dipole experiences a torque. Two equal and opposite forces acting on a dipole will rotate the dipole, and that we call it as the torque. Now, the torque on this magnetic dipole due to the external magnetic field is given by the expression tau is equal to m into b multiplied by q into r, mb into qr, where m is mass of each dipole, b the magnetic field, and qr is this distance, right? And qr will be nothing but equal to 2l sine theta. It will be 2l sine theta, where L is the magnetic length of the dipole, PQ is equal to 2l, shown in figure. Now QR will be therefore equal to 2l sine theta, and PR will be equal to 2l cos theta if required, the other component of 2l, right? Now therefore tau is therefore equal to mb multiplied by qr is equal to 2l sine theta. It is 2l sine theta, qr into 2l sine theta, and 2l into m is taken as equal to mu m. 2l m is taken as equal to mu m, and that we call it as the dipole moment, mu m, multiplied by b sine theta. Tau is therefore equal to mu m b sine theta. Tau is the torque acting on the magnetic dipole due to the presence of the external magnetic field B. Now, the potential energy acquired by the dipole because of the torque, because of the rotating force, because of the magnetic field, right? And that potential energy is given by the expression A equals integral pi by 2 to theta tau d theta. This is the expression for the potential energy of the dipole in the presence of external magnetic field because of the torque acting on it. So substituting for tau, tau is mu m b sin theta. So d theta ಏನಿದೆಯೋ ಅದು ಹಾಗೆ ಇದೆ. So on integrating and substituting the limits of integration upper and lower, we get A is equal to minus mu m b cos theta. Minus mu m b cos theta gives the potential energy acquired by the dipole. Therefore, N is, we know that N is equal to C exponential minus E by kt. C exponential minus E by kt is N. Therefore, substituting for E, we get N is equal to C exponential minus of minus plus agide, right? E is mu m b cos theta whole divided by kt. Let us now differentiate this expression N. Differentiating this, we get dN is equal to C exponential of mu m b cos theta by kt hage ide. Now differentiating the terms within the bracket, we get mu m b by kt, again a constant. Differential of cos theta is minus sin theta d theta. Now rewriting this expression again, we get C naught exponential of this into sin theta d theta, where C naught is minus C into mu m b by kt. Minus C into mu m b by kt is taken as equal to C naught, which is another constant. Now, the dipole moment is obtained, the average dipole moment is obtained by integrating the magnetic dipole moment between these two limits, between 0 and pi. And the average magnetic dipole is given by the expression that it is the ratio of total dipole moment to the number of dipoles present. Total number of dipoles to the total number of dipoles, total number of dipole moment to the total number of dipoles gives the average magnetic dipole moment, and that will be equal to total dipole moment will be equal to integral mu m cos theta dn gives the total magnetic dipole, and number of dipoles is given by the integral 0 to pi dn. So substituting for dn in the numerator as well as in the denominator, we get, right, mu m cos theta hage ಇದೆ, ಏನು ಚೇಂಜ್ ಇಲ್ಲ, ಮಿಕ್ಕಿದೆಲ್ಲ ಟರ್ಮ್ಸ್ ಕೂಡ they are related to they are corresponding to dn. Similarly, in the denominator we have substituted for dn. Now taking mu m b by kt as equal to alpha, mu m b by kt as equal to alpha, and also I take cos theta as equal to x. And differentiating this, we get minus sin theta d theta is equal to dx. So substituting for these in the above expression, we get also the limits of integration gets changed. If theta is equal to 0, we get x is equal to plus 1. If theta is equal to pi, we get x is equal to minus 1. The limits of integration also gets changed. Therefore, mu m is taken out as constant, mu m into integral plus 1 to minus 1. Substituting for all these values, we get x into e power alpha x dx. Similarly, in the denominator, integral plus 1 to minus 1 e power alpha x into dx. Now rewriting this expression, again rewriting this, we get mu m into integral plus 1 to minus 1 x by alpha into differential of e power alpha x. Similarly, in the denominator, integral 1 by alpha into differential of e power alpha x. These alphas gets cancelled since they are constants and taken out. Now integrating the numerator as well as the denominator, we are integrating this, alphas gets cancelled. On integrating this, we get this, and substituting the limits of integration, finally we get this expression. And this term will become equal to cot h alpha. Cot h alpha. Therefore, mu average is equal to mu m into this whole term is taken as equal to L of alpha, where L of alpha is cot h alpha minus 1 by alpha, and that we call it as a Langevin function. Langevin function. When all these n number of dipoles are aligned in the direction of the field, then we say that the paramagnetic substance is said to be magnetized. Is said to be magnetized. So the magnetization becomes, the magnetization of the paramagnetic substance is given by the expression m is equal to ms into L of alpha. This gives the magnetization of the paramagnetic substance when all the dipoles are aligned, when n number of all the dipoles are aligned in the direction of the magnetic field. Therefore, this can be again rewritten as m by ms is equal to L of alpha, but L of alpha is equal to cot h alpha minus 1 by alpha. Now, at higher temperatures and moderate values of B, the value of alpha will be very small. For small values of alpha, cot h alpha becomes equal to this. It is a progressive expression. And we neglect the higher powers of alpha. We neglect all these alpha values and we consider only these two terms. And rewriting this, cot h alpha minus 1 by alpha will be therefore equal to alpha by 3. Therefore, this expression becomes m by ms is equal to L of alpha, that will be just equal to alpha by 3. Or m is equal to ms alpha by 3. m is equal to ms alpha by 3. The slope of this Langevin curve is 1 by 3 when alpha is small. When alpha is small. For small alpha, the slope of Langevin curve will be just 1 by 3. Now, therefore, the susceptibility is given by, susceptibility is equal to m by h, but m is equal to ms alpha by 3 multiplied by h, and therefore ms, but we also have ms is equal to mu m into n, and alpha is equal to mu m b by kt. Substituting for ms and alpha in the above expression, we get the susceptibility of paramagnetic substance is equal to ms alpha by 3h. That will be equal to, for ms we have mu m into n by 3h as usual, and for alpha we have mu m b by kt. Simplifying, we get mu m square n. For b we have written mu naught h, in the denominator it is 3h kt, h again gets cancelled, therefore it is mu naught mu m square n mu naught by 3 kt. But we also have xi of p equals c by t, and that will be equal to this. Therefore, as t is there in the denominator on both sides, therefore c will be equal to mu m square n mu naught by 3k, and which is called the Curie constant. Right, one more c, where n represents the number of atoms, and if n is equal to 5 into 10 power 28 atoms per cubic meter, we get xi of p equals, and k is Boltzmann constant, mu naught is permeability of free space, and substituting all these values, we get xi of p equals 0.3 by t, and at absolute temperature, that is 300 Kelvin, xi of p will be equal to 10 power minus 3. Xi of p will be 10 power minus 3. And this completes the Langevin's theory of paramagnetic substances. Thank you.